Let's wrap up with sections 9 and 10. In section 9, we'll talk about the top-level block and its architecture. In section 10, we'll summarize a dozen guidelines for writing SystemVerilog code in an XMODEL-based verification flow. Here's our top-level block. For simplicity, we made it a simple module, a portless module called envmod. And as the name implies, it sets up the environment surrounding the DUT, all the components needed to fully test the bandpass filter. At the higher levels, it constructs objects like driver, monitor, and scoreboard, as well as the mailboxes connecting them. At lower levels, it instantiates the interface buses and the fixture, which in turn contains the DUT. This top-level module also generates the packet clock waveform and an asynchronous active high reset pulse. In a more UVM compliant test bench, this environment would be a class derived from UVM env, and its main advantage would be that you could top-down configure all of the components underneath it. We don't need that complexity, so we went with a top-level module. And the most important code in our module is this initial block. It carries out our entire test in UVM-like phases indicated by these green comments. We covered our test case in Unit 6. If you recall, we began by running 16 or more iterations, applying random frequencies and modes to the DUT inputs and measuring its response. And we then powered down for several cycles, went through a one-cycle wait state, and then resumed filtering operation for a few more cycles. So all that is carried out by calling these various tasks. Starting at 0 simulation time, we run the build task. It's not shown here, but it simply calls the new constructor for all of our objects. Remembering for the case of the monitor or driver to include as an argument the name of the corresponding interface bus, which connects to those objects using a virtual abstraction. Once that's done, all the components are in place. We're ready to advance time. The top-level block generates an active high reset pulse, and we wait for that to be over, and then we launch the body task in the sequence object. We saw that in section 3, and it generates data packets and sends them through the mailbox to the driver ready for use. Here's where we do most of the real verification work. We concurrently launch the driver task apply sign to apply, based on the data in the packets, apply the next random sinusoid to the filter's inputs and a random mode. And later in the same clock cycle, we want the monitor to sample the peak-to-peak output of the filter. They have to be concurrent because we want to measure that amplitude while the input sinusoid is still being applied. At that point, we're done advancing time. We can transition to check phase, where we put the scoreboard to work. Its score packet task, as we saw briefly in section 5, takes the data packets sent up from the driver and monitor, uses them to compare the actual filter gain versus the expected filter gain derived from a golden HSpice reference model. And that happens in 0 time and generates a transcript, which we'll see on the next slide. We can then call $finish. The simulation run is over. Here is our first look at the XMODEL command line. For readability, we've placed it inside a manifest file. This has a few more options not shown here to avoid clutter, as well as all the source code files would be included in this single manifest file. Using various XMODEL options, we can specify both compile time and runtime options. So for example, we're specifying a total simulation time of 200 milliseconds, although typically we'll $finish before that time. Then per our guideline number 10, We're reducing the verbosity of the assertions we incorporated in this test bench by telling the simulator to be quiet. We rely on the pass and fail display tasks to tell us what happened with the assertion. We can also use a runtime assertion to generate a random seed that'll govern all of the $randomize calls. This is going to be simulator specific. Here we're using the VCS native test bench random seed option. By the way, the double dash is part of the XMODEL syntax. Since you can embed more than one option on the same line, this tells the parser you're done. The seed is not explicitly shown in the transcript, so we hit on the practice of embedding the seed value within the name of the log file that SystemV prints out. So using this initial block, we can build all the components in our environment and begin from the data packets, applying DUT inputs, sampling the DUT outputs, and scoring the actual versus the expected results. Here's a typical transcript. This one took 180 packets. We're looking at just the last two. For example, packet 179, we first confirm that the packet IDs match. And in this transaction, we're applying a randomly chosen 34 kilohertz sinusoid to the DUT inputs in mode 6. And we then print out the actual filter gain and the expected based on HSpice data. The discrepancy is pretty small, less than 0.5%. And even over this long run of 180 packets, the worst case discrepancy was less than 2%, 1.7% to be exact. Using the random seed and changing it from run to run, you really get maximum reuse out of this OOP test bench code. Every time you vary the seed, you're getting a different mix of input and output data, fully verifying the DUT in all of its modes. That's the end of our webinar. Let's go on and summarize the dozen guidelines. Our number one guideline was to use the XMODEL library primitives to generate a simplified macro model early in the development of the test bench. We used this to begin developing the test bench even before the DUT was finished. And the macro model is easy to cobble together. We used, instead of the transistor level op-amp with its 9 CMOS transistors, we used a simple voltage-controlled voltage source with high gain to model the op-amp, and then the CMOS transmission gates were modeled using a simple resistive switch. And this enabled to begin debugging the test bench even before the DUT was fully designed. And we could be sure, using the simplified macro model, that any issues that came up compiling the test bench lay in the test bench code rather than in the DUT itself. Then when the transistor level DUT was complete, we just plugged it in into a working test bench. Guideline 2, as we've mentioned in previous sections, we found it very useful to encapsulate all analog specific elements, X-real signals, X-bit signals, even analog assertion code inside a fixture submodule that we instantiated in the top level block. And this refers back to slide 28. Guideline 3, in this part 2 tutorial, we used a UVM-like sequence object to do all the test writing. So all of the randomization is contained in the sequence block, and that maximizes reuse because a test writer engineer can write this untimed sequence without intimate knowledge of the detailed DUT timing or pin names. Guideline 4, as we just saw on slide 74, It's essential to run the apply sign task from the driver concurrently with the monitor PPA task. Whereas in a digital design, you usually have a luxury of registering the digital block's outputs. Here we're looking at an analog block, and we need to measure the output voltage while the input sinusoid is still being applied. So fork join was the way to go. Guideline 5, we saw that with a small number of modes, 8 in our case, you would by default get a lot of repetition, like 3 M0s in a row. In a simple case, we could use RAND-C to give us cyclic randomization, but it has limitations. It's not very scalable, and it has little persistence across packets. So as on slide 22, we used a static queue to keep track of the used modes with a constraint forcing the solver to use unused mode values until we began a whole new cycle of 8. Guideline 6, we just saw how to specify a random seed on the command line. That's really the easiest way to control randomization. SystemVerilog has a lot of fancier features like the sRandom method, which allows you to specify a random seed specific to an object or thread. But for a simple DUT like our bandpass filter, this was a much easier approach. Guideline 7, coverage. In a UVM compliant test bench, all of the cover groups and cover points would likely go within a dedicated class called coverage. We found it easier to put the cover group inside the monitor class. However, keep in mind, it still has to be constructed before you can gather coverage data. Guideline 8, we saw using an if and only if clause in the coverage code to avoid sampling while the DUT is in bypass power down mode. Guideline 9, we saw how to sample cross coverage of 2 input variables, the mode and the frequency, and that gives us confidence that we've fully covered the DUT operation, and that in mode 0, say, we cover the whole frequency spectrum, not just maybe the high-end frequencies. Guideline 10, this keeps assertions quiet and relies on our custom pass and fail tasks to print out information every time an assertion passes or fails. Guideline 11, we can use a default disable clause for assertions, especially if we have multiple assertions, to make the code more concise. You can specify a default clock and a default disable for asynchronous resets. Finally, guideline 12, we used enumeration a lot, not only for the states of our test case, but also for the modes. And it makes the code more readable. It's visible during a simulation run in wave view. And also, coverage bins are automatically created based on the enumerated names. And that's our webinar. I hope you found it informative. For more information, you can check the published tutorials under the ResearchGate site. Here are the URLs. And you're welcome to visit the scianalog.com website for more information on XMODEL capabilities. We'd like to thank the IEEE for sponsoring our webinar, and best of luck verifying your on-chip analog IP block.